Hello and welcome back to our Guardrail training. This is Module 4, where we will review our new length of knee design tool, which is an Excel-based program for helping to design guardrail layouts that we've discussed earlier in our training. And we'll also take you through a couple examples before the training is complete. So the first thing you might ask is, well, where is this Excel program located? Again, it goes back to that one-stop shopping where you go to our design standards homepage, both the DSR website as well as the standard ebook website, laid out in the same way, where you have the design standard index here, and then as you go from left to right in the columns, you see our IDS instruction for design standards, and here's our design tool. It says XLS because it's an Excel program. I'm going to now bring up the Excel sheet just to walk you through it. Alright, so here we are looking at our Guardrail Length of Need program, version 1.03. As you can see, it's just an Excel spreadsheet, but we've gone to some links to have all the accurate calculations in there and to try to make it as easy as possible. Our goal is to have it be user-friendly, so we always welcome feedback on that. First, I'm going to just kind of walk you through all the tabs and so you can see the parts and pieces just to get a feel for it, get a feel for the overall scope of the program and the types of things it handles. And then I'm going to focus in on part A and B so you can get a feel for the workflow. Part A and B, which is essentially the sheet we're looking at now, is the one that, believe it or not, is a little bit more complex because you have to decide if you're going to use part B or not. But just starting with a broad overview. Here we have part A. So we've seen this drawing before. This is our standard length of need drawing where things are pretty simple. You can just put a trailing anchorage on there, and so you're just designing to shield a hazard on the side of the road, and you're putting in some length of guardrail. And then scrolling down, we then have a part B, which is an extension of part A, depending on whether you need it or not, depending on if you have a two-way, two-lane road and traffic coming the opposite direction. We'll talk a little bit more about that in a moment. So that's what's on tab 1. That's your basic type of design configuration for tab 1, is just shielding a roadside hazard. Part C and the second tab shows our crossover guardrail configuration. This one has a crash cushion on it. The next tab covers the approach terminal version. And so it looks like there are, a few more variables here than are involved in the simple roadside hazard version. But the good news is a lot of these items are just default values. We actually explain in the comments exactly what value you'd want to fill in here based on whether you're working with TL3 or TL2. And so it's pretty convenient. And the good news is it's a one-step process. You put in your design variables, you put in your stationing, and then you get the outputs, and it gives you 4 station and outputs representing this point, this point, this point, and this point. And by using those station and offsets, you can go ahead and put those directly in your plans and lay out your guardrail, and the contractor can build it. And so it's really a one-step process for something that looks pretty complicated. These would be the equations that are used to calculate length of need. Call this the unified theory of guardrail. So internally there are a lot of calculations going on, but for the designer, we're hoping to keep it simple and straightforward. And we'll go more into detail of that. We're going to do an example that looks just like this layout right here. Okay, so here's the same thing. You have your narrow median, and it's your crossover guardrail. This time you have an approach terminal. The end variables are slightly different, and so we just want a whole new drawing to keep it simple. The inputs are just slightly different here, and rather than have them be confused, we just have 2 completely different tabs for each condition, whether you have an approach terminal or a crash cushion on the previous tab. The next tab is a simple connection to a rigid barrier where you're just running some length of guardrail along, and you have the hazard. Now the hazard that you're shielding could be behind the rigid barrier. When I say behind, I'm talking about traffic coming from right to left. This would be behind the rigid barrier. It could be out in front of the rigid barrier. All that relative stationing is built in, so you essentially input the station of the face of the rigid barrier, you input the station of the face of that hazard, and then the program will automatically know where the two are located relative to each other and how long your guardrail has to be, essentially what station post 1 has to be at. And so that tab handles this type of design. Roadside design guide data. This is that AASHTO table we had seen back in the IDS portion, were based on your ADT and your design speed. You're then going to grab those values for runout length. The program automatically does that, but this is just showing you where the data is grabbed from so you can see that. Here we have some policy information. We explain the design basis, where we say that, this method is essentially based on the AASHTO Roadside Design Guide 4th edition. And then we also have a design tool note. All of our FDOT software, it's designed to be left open so that the engineer can see the calculations. And the idea is that you would have some idea of an appropriate design, and you can check the output. And so it's saying that the department is essentially not responsible for what shows up in your plans. That really is the engineer's responsibility, but the design tool is here to assist the engineer. Here we have the version history. As you can see, we're already on version 1.03, and so as we make little changes here and there, we explain what our changes were. As updates are required, or we get questions about things, we can add clarifications or just correct things and improve things in general. And so we keep track of our vision history on the last tab if you're interested to see what types of things we're updating. So one other thing I wanted to mention is that in general, as far as connecting to a rigid barrier as is shown, this generally right now is set up for new construction where these rigid barriers are considered new and where the approach slab is considered a new design, where essentially the concrete barrier runs the entire length of the approach slab and there's no interference from any existing structures. That's when these type of calculations apply. And so that would be limited to index 400. Where 402 for connecting to existing bridges and existing railings would still use the old design tools, the old design table to come up with guardrail lengths. And that's just temporarily because right now this is a new method we're moving towards where the designer has the control. The designer ends up coming up with the length of need and putting into the plans exactly what's needed per roadside design guide. But there are simply too many combinations of existing bridges in index 402 to cover that all right now. And so our next large guardrail project will be to make all of the index 402 for all existing bridge items compatible with the calculations in the way we do index 400. So temporarily, index 400 calculations will be different from existing bridge type scenarios in index 402. And I just wanted to point that out. Okay, what I want to do now is take you through the workflow of the first tab here. And again, that's our simple roadside hazard shielding. And it is a two-step process. And so because of that, I just wanted to show you a little bit more about how that would work. So essentially, first thing you do is design your traffic as though it's coming from right to left here as it's shown drawn. You put in your direction of your traffic for the relative stationing, ADT design speed, your station of your hazard, your basic variables, and we'll cover this as we go through our design example coming up next. But you'd input the variables and then you get some preliminary outputs. And now you go down to the bottom of the Excel sheet and essentially we're skipping over right now part B. And we say, no, we don't need it. Everything's not applicable. Then you get your design outputs. So if the only condition you had was a roadway and you're shielding a hazard on the side of the road, this trailing end is not in the clear zone of any opposing lane, so you're not worried about two-lane, two-way roads. It's the most simple configuration you can have. Only part A. You can go ahead and skip to the end, and it will give you your station and offset for the primary approach terminal, and it gives you your station and offset for the type 2 end anchorage. You see this last part's just not applicable. So now, if you do happen to have a two-lane, two-way road, you see part B is for the opposing direction, if applicable in red, and this is considered the part A extension. So if required for a two-lane, two-way road with a hazard in the far lane's clear zone. So this is considered the far lane. This hazard would be within the clear zone. And if that's the case, I can show you what happens. It says, is part B required? You go ahead and toggle it to yes. Now everything that was not applicable before then populates because now you're using part B. So that's essentially how it works. Then you'd go in, put in some of your similar variables to part A. And now when you go down and look at the end, look at the outputs, you see the type 2 anchorage, it says is no longer applicable. That's NA, NA. Now you have a secondary approach terminal and it gives you station and offset for those things. And that takes into account the length of hazard, so it extends the guardrail automatically. It takes the stationing from part A and then uses it to calculate essentially what's a trailing end station in part B, only this we know that this is an approach terminal for the traffic coming from left to right here. And so that's all I wanted to show you on the first tab, just so you have an idea for that workflow. As I said, this crossover guardrail looks a little more complex, but it's really not, because it's only a one-step process. You don't really have to make any decisions. You just put in your inputs and you go ahead and you get your 4 outputs of station and offset. And so with that, we're going to go back to the PowerPoint, and then we'll talk through a couple of design examples to give you guys a feel for this. Okay, so now we're resuming with our PowerPoint. We can talk through some of these input variables. This drawing you see here comes directly from the Excel sheet, and so it's helpful to look at when you're trying to follow along. Okay, so the first input you're going to be asked is the direction of the near lane traffic, and so this would be considered the near lane. That's as opposed to the far lane for a possible two-way, two-lane road. But for this case, we're just going to be focusing on a single lane for now to keep things simple. So you see the arrow is coming from right to left. If you're looking at this in terms of it being north as being up, then that would be westbound. And so you can go ahead and, it's a toggle. You can pick which direction you want the traffic to be going in for the relative stationing calculations. You're going to eventually put in the station of the approach face of this hazard, and so then everything else in terms of the outputs gets based on that input station. And so picking the direction of traffic is important. The drawing will stay fixed the way it is, but you will just know as a designer which way the traffic's going, and you can check the stationing to make sure that it makes sense as far as an output goes. We thought that was the most simple way to establish that input for relative stationing, is just a direction, because it's so easy to check that the station is going in the direction that you want it to for your guardrail for shielding a hazard. There are some strange cases where, for example, what's considered an eastbound roadway could actually be more headed north, and so on. And so we really don't need to get too hung up on that. It's just, you know, whatever direction in here is going to give you your stationing direction that's required to extend the guardrail out in front of the hazard, given that you know which way the traffic's going. That's really all there is to it. So it does require an engineering check, knowing that when you're going from west to east, the stationing is going up. When you're going from south to north, the stationing is going up. And so that's the way it works. So the second input is ADT in vehicles per day. That would be for the total roadway. The design speed in miles per hour. It's not the posted speed, it's the design speed. The approach face of hazard station that we just mentioned. So that's what the rest of your stationing outputs get based on. It extends the guardrail essentially out in front of the face of hazard station, assuming that the traffic's going from right to left. The length of hazard, LH, that's important because your guardrail then extends that length of hazard to continue to shield that hazard. And then after that, the software will automatically add an additional 6'3" to account for that trailing anchorage length in order to tie down that guardrail, establish the redirective capability. And so the length of hazard is important, and that would also be important if you're going to use Part B. The lateral area of concern is the lesser distance from the edge of traffic lane to the clear zone limit or the back of hazard. So if you remember, we're trying to design, guardrail in the most efficient way possible. So basically we're saying we don't need to design it any longer than we have to. If you have a hazard where the back edge of it is only 15 feet off the roadway and your clear zone's 26 feet, you don't have to design for the full extent of that clear zone. You just only design to the back of hazard, and it will make your guardrail considerably shorter. The next input would be the lateral offset of guardrail, LO, so it's almost like the original offset. And so that's your general offset of guardrail for your typical section, likely per the PPM. And that's prior to any flares. Here we have it shown just right next to the hazard. So that's your LO. It's kind of like your guardrail starting point prior to the flare. Length of gating, LG. That's this breakaway portion that we had discussed in the IDS. And so you want to account for that and know how much of that guardrail is going to break away. Typically, that would be 12.5 feet or 12 foot 6 inches. Most APL drawings have that unless you're using a non-gating terminal. Then LG would be 0. Terminal flare at post 1. We let you know that would be 4 feet, and that is located at post 1, not to be confused with where Y is located. That's why the name includes at post 1. And you know, again, per the design standard, we have a 4 foot max that's allowable. So here we're actually showing that flare. The flare is measured between the face of guardrail, that point where LO is, and then at post 1 what the face of guardrail would be. So that difference would be the flare. And then the flare taper length, this is used for calculating, basically backwards calculating Y. So you're going to put in flare because you know what's allowed, that's at post 1. This will back calculate Y based on what your LG is. So that's the offset that's used in the calculation, basically where your redirected portion of your guardrail begins. And so that's what that is. The default value is 35 feet. This value, basically the taper length, is a little different for every APL drawing. 35 seems to be about the average, and that's accurate enough for the purposes of these types of calculations. So moving into our first example, based on the variables we've just seen. Now, it may be helpful for you to have some type of printout. I think we can attach it. I think we can go ahead and add something to the end. We'll call it the paper program. The alternative is to just look at the actual Excel program as we're doing this and print it out. But the idea is that it's nice to have this drawing in front of you as well as these variable definitions in front of you when you're trying to make these decisions. And so for now, and to make it a little bit easier, I'm just going to walk you through these variables of these design examples and just define them for you and give you the answer. So we'll go pretty quickly, but if you do want to go more slowly to know exactly what it is I'm talking about and how it corresponds to that drawing, it'd be helpful to have that drawing on hand. And so when we visited all the districts in person, we allowed the class some time to try to fill in all these variables themselves. But through a webinar, we really don't have a way to do that. So I'm just going to go ahead and talk you through it and see what you can pick up. And you can try it again on your own if you like and see where the answers came from. So some of our program inputs, well, I know you put in design, speed, and ADT and things like that. Those are straightforward. It's almost, you just copy it right out of whatever is given or whatever you have for your roadway. So the direction of traffic shown here, that's the first input we'll cover. And one other thing I want to mention, and it's a good time to bring this up, is we're only now concerned about this lane. So for part A, the first thing you're looking at is the nearest lane to your hazard. You're considering you have a simple case. You're not really concerned about the downstream yet. You're just covering, okay, what's my nearest lane? And then we're designing for, when we're finished, we're going to have the stationing and offset to fill in this call out right here. So that's our goal. So looking through these examples, we're going to have blank call outs, and that's what we're trying to design. So we're concerned with this guy. We know we've got this hazard information, and we're coming from right to left. Now, what's our direction of traffic coming from right to left? Okay, we put a north arrow there. So from that, you can figure out we're westbound. What's our length of hazard? Okay, 35. Pretty straightforward. We put a nice label there so you can see the hazard. Longitudinally, it's 35 feet long. And that's helpful for the design of all this extra length of guardrail that's beyond the length of need. What's our lateral area of concern? LA. Okay, so we have 26. Now, you say, how do we come up with that? We're coming from right to left, and, well, okay, we know our clear zone is 30 feet. Clear zone's measured from the edge of the travel lane we have here. And so, okay, that's the first thing to consider is this hazard within the clear zone. Now, the back of the hazard, as compared to the edge of this traffic lane, is at 38 feet, but that's measured from the center line. So the back of the hazard is actually, since it's measured from the center line, everything with ASHTO is measured from the edge of the traffic lane that we're designing for. So you take that 38 feet and subtract 12 off of it, and that gives you 26. And that would be where our back of hazard is. Our back of hazard is 26 feet away from this traffic lane coming from right to left. Just to make you guys think a little bit, that was one to make them think in the classes. So they had to think, okay, where's our center line of roadway? And how do these station and offsets work? When you're designing your plans, obviously the information comes to you in different ways. For the most part, to be honest with you, in your plan, it would actually be more simple because you'd say, here's my traffic lane, and you use your CAD tool to measure the distance to the back of the hazard, and you just get it. But here, it got a little tricky. So anyway, the back of the hazard we know is 26 feet from the edge of this lane. Our clear zone is 30 feet. Now remember we said our lateral area of concern, you only have to design for the lesser of the two. So LA, the back of the hazard, is 4 feet closer than the back of our clear zone limit. And so to design the most efficient guardrail, we don't need to go to the entire extent of the clear zone. We just go to 26 feet. That could save us, a decent amount of guardrail. So LA will make 26 feet. The approach face of the hazard station. Okay, we've called it out. So we want to know what station is that approach face. And it's at station 100. And so we just went ahead and gave that to you. That's what all the other calculations will then be based on. The original guardrail offset, LO, that equals 10 feet. So that's essentially, like I said, that's your typical guardrail offset per the PPM prior to any flares. Basically the original guardrail offset, 10 feet. We got it called out there, right there for you. Length of gating, LG, well, we've said that the terminal type is gating. The default value for gating terminals is 12.5 feet. So we'll go ahead and just put in 12.5. Flare at post 1. Okay, we've given our flare value. Our flare equals 4 feet. That's the maximum allowable by the index. That's pretty common. And so we just went ahead and put in 4. And the program can take care of the rest. Okay, so we get some preliminary outputs. We get the Y value. That's at post 3, 12.6 feet from the edge of the roadway. We get a run out length. That comes out of the AASHTO table so you can check it. Some designers, will just do this simply to grab that length of need value. Once they got 113.6, they can go around and play with this in any way they can. They can put in their guardrail, extend it just visually past the hazard, make sure it goes 6'3" past it, and then they know the guardrail's designed. And that might be more simple for some people just to go ahead and grab the length of need. And that's why we gave that, just a raw output. And so anyway, these are unadjusted stations. And by unadjusted, we mean it doesn't round to the nearest 6'3" inch panel length. Okay, so that's really the end of part A. And now we have the consideration. We say, okay, we got all these question marks here. Can we just go ahead and put a type 2 trailing anchorage on there and call it a day and be done with this? And so we have to give it some thought. All right, well, we know our clear zone is 30 feet. And so the clear zone would be measured basically from the center line of roadway, which is the edge of this travelway that we're concerned about. We're concerned about these cars and these vehicles coming from left to right. And so coming from that direction, it looks like that's only 22 feet away. And so that's well within the clear zone, the back of the guardrail. So, and that's one thing you have to understand, even if the hazard is not within the clear zone, if the end of the guardrail is within the clear zone, you can't just put a type 2, you have to just put an approach terminal on there. So we know we're going to need an approach terminal just for that reason. Now let's check if the hazard's within the clear zone. Okay, so 12 plus 10 is 22, 5 feet. So that's 27 feet away. We know the clear zone's 30. So the clear zone falls in the middle of this hazard somewhere. And so we know that hazard's within the clear zone, or at least a piece of it is. And so the answer is yes. For the purposes of education, it just so happens that we're going to need to do part B. So go ahead and move on to part B. These variables now, coming from the opposite direction, are all pretty similar to part A. So we won't really walk through all these. We're just going to go ahead and jump into the design example, and I'll talk you through those variables as we do them. All right, so we've moved on to part B. Now this is considered the far lane. That would be the near lane. We've already designed for it. Now here's the far lane. As I've said, we're designing now for that call out that's blank. So when we're done, we're going to have the information to fill in that call out and go ahead and talk you through some of these program inputs. So the first one is part B required. It's a toggle switch. We already established that. Yes, it's required. So that would be circled. Lateral area of concern, LA. Okay, well, how do we come up with this one? Well, believe it or not, this offset call out is more convenient when you're designing for this lane coming from left to right, because the center line of the roadway is the same as the edge of the traffic lane. And so you know that, all right, the back of that hazard's 38 feet away. Now, the clear zone is only 30 feet. So we know that we only need to design for the lesser of the two in order to design the most efficient guardrail system. We don't need to go any longer than we have to. And so the lesser of the two between 38 and 30 is simply 30. So that would be our lateral area of concern coming from left to right. The original guardrail offset, LO. Okay? Now, rather than in the Excel sheet put in lane widths and where the center line's located and all these different things, we're going to keep it simple, just like AASHTO does it. And whatever lane we're designing for, we're just going to measure from the edge of that lane. So in this case, it's 12 plus 10 equals 22. It's not just 10, because we're talking about now the lane we're designing for, which is the guys coming from left to right, basically eastbound. So that LO is 22, 12 plus 10. Length of gating, we still have a gating terminal, that's given, so go ahead and say 12.5. Flare at post 1, just to switch things up a little bit. We've said that the flare here will equal 0, just to show you that you can not have a flare if you want to. It could be that you have some clearance concerns here, you're trying to minimize the space requirement, who knows why, or a flare won't make that large of a difference for such a short run, and so you just want to keep it parallel to the traffic because it happens to be far away from the approach lane anyway. And so anyway, so we'll go ahead and say the flare is 0, and so that would be the last input here. And so your program outputs, it's going to go ahead and give you Y. Y is the offset from the traffic lane at post 3. Now Y, that 22 is the same as LO. That's because there's no flare. So it's the same, you can see it's the same. Then we have some more preliminary outputs. It gives you some unadjusted stationing, but that stationing has not yet been adjusted to the nearest panel length. Okay, so now we're finished with part B. Okay, so here we have our grand result showing the output summary from parts A and B. You can see that we filled out our callouts up here in both locations. That's based upon the information we've received from the outputs of the program. And so I guess the first thing we can look at is our primary approach terminal. It's for the vehicles coming from right to left. You can see that's at station 101 plus 28.7. We went ahead and filled that right in. And then we also have the offset, which is provided by the program. Now, just as in keeping with AASHTO, how everything's measured from the edge of the traffic lane, the program continues to output things measured from the edge of the traffic lane. And so you can see that's a 14-foot offset, but if you add in the distance to the center line, it then becomes 26 feet. And so that's basically how it works. Your CAD tools will actually tell you that offset. If you just went ahead and put that point in there, you knew where your guardrail would be. If you put in your station and put in what your flare is, your CAD tools would then give you the offset. Your secondary approach terminal, which you remember comes from part B, as it says down here. It's located right at this location. That's handling the traffic that comes left to right. So that station's 98 plus 91.2, just as the program had output. And it's showing the offset from the nearest travel lane. So in this case, it shows that 10-foot offset. And so you can see because it's a parallel terminal, it's the same offset as the original offset right here. The difference between the two is 4 feet. One is flared, one is not flared. Now we do the best we can with the output of the program, and the program does have to assume that the roadway is essentially going in a straight line. The center line of the road is straight without any curvature effects, such that when you subtract one station from the other, that basically gives you your total length of guardrail. And just based on that philosophy, the program will automatically design this to the nearest 6'3" panel length. So it tries to be helpful to the extent of the capability of the program. When you start adding degrees of curvature, the calculations become much, much more complex, and really that's not necessary. So the program does not account for curvature. So the idea is that we provide a range. And if you provide your guardrail in the plans outside the limits of this range, so the starting and stop points are outside of this range, so they would be greater than or equal to 101 plus 28.7 or less than or equal to 98 plus 91.2. That would be your start and your stop points. Then that's considered acceptable. That meets your length of need requirements. And so what you would do is in your plans, you draw your guardrail to outside of these range limits. And that gives you some flexibility because when you extend your guardrail to go to the nearest 6'3" panel, you can go one way or the other. You can go, depending on which wave of traffic you're talking about, you can go upstream a little bit further or downstream a little bit further of that hazard, just whatever happens to fit into your project. But the whole goal is to get to the nearest 6'3" panel length increment, and that can help out contractors and help them plan a little bit better, particularly if you're in an urban setting and you want your guardrail to end in an exact location. For longer runs along a freeway, remember we have that tolerance of plus or minus a half a panel length. So it's not as critical, but when you're in a really tight area and you're trying to make the best use of your space, you're going to want to place it in the plans, the way it's going to end up looking in the field. And in order to do that, you design it to the nearest 6'3" panel multiple. And so again, to touch on the concept of curvature, you know that if you happen to be on the outside of a curve, let's say you're 50 or 60 feet away from the center line, your station to station would end up being a lot shorter length if you were just to do the subtraction between the two versus the actual length of guardrail that might be on the outside of the curve. And so what happens is you could end up with guardrail that's a lot longer than just simply subtracting one station for another. And conversely, if it's on the inside of the curve, it could end up being a lot shorter than the station to station. Luckily, we can get away with just providing a simple range, assuming it's linear, because if the guardrail is on the outside of the curve, it should be getting longer anyways to compensate for that curve, and it adds a little bit to the length of the guardrail, which is helpful, and that's what it should be doing. And then if it's on the inside of the curve, it'll get a little bit shorter, but the vehicles in general won't be driving in the direction of the hazard anyway, and so it's okay to make the guardrail a little bit shorter than the station-to-station calculation. So that's the idea behind that. So that's why we simply provide a stationing range, and then your guardrail should just extend beyond those limits in either direction. Alright, so now we're going to move along to our Part D example, showing twin bridges or sister bridges with a narrow median. And this is, considered our guardrail crossover configuration, where the guardrail is actually starting to cross over the median. And again, the idea is that rigid barrier for the opposing lane is actually considered a hazard, and so you're trying to shield against that. And so the main direction of traffic that you're designing for is coming from right to left. And so with that, we can start walking through some of these variables. The first few variables are very similar to Part A and B. So you'd say, what is the direction of near lane traffic? Edge of near traffic lane is labeled up here, and you have your arrow. And so this is the traffic that we're focused on. And so you go ahead and put in that direction of traffic. The ADT, vehicles per day, up in these lanes that you're designing for. The design speed, as you know, not posted speed, the actual design speed. And then you have the begin and end rigid barrier station, and that's at the guardrail connecting location. So that's not to be confused with this hazard point. That's where the guardrail actually connects. And so the first thing you're going to start off with is saying, okay, well, I have a bridge located here. The rigid barriers are required to be at these points. Where does that rigid barrier end? And you're just concerned with the end face. Not really where the begin and guardrail station is, because the program will calculate that for you. You can see it's slightly different by 7 1/4 inches. You just put it in the face of the rigid barrier. And so that station goes in right there. The lateral offset of the guardrail, LO, as you can see, it's called out right up here. And that's really a distance that your shoulder line is offset from the edge of the roadway. Just continuing along here. For the purposes of these calculations, you can consider the toe of the barrier and the face of the guardrail to be the same. If you like, it's close enough. And so that's really like the starting point offset of the guardrail prior to any tapers or flares or things like that. So that's similar to Part A and B as well. The lateral area of concern, LA, well, if you're designing for this hazard, considering that the rigid barrier here is the hazard, then really it's the face of the rigid barrier for that opposing lane, really the toe of it, so the extreme point. So you can see LA is measured all the way to the back edge of it, and that would be considered the back of your hazard. And so typically LA would equal that distance right there if it happened to be within your clear zone. So we got LP1, that's the parallel approach transition length. And so this right here is actually something that's derived from the standard. We give those values to you as defaults, and so that's kind of convenient. If you happen to have a TL3, then we tell you that default length is 27.5 feet. For TL2, it's 18.2 feet. And that length is measured from the end of the rigid barrier, and we let you know that in the note, not the begin end guardrail station. And we do have a handout that we had provided in our trainings when we visited the districts that explain how we derive these lengths, just looking at the standard. You probably could figure it out for yourself. I think we're going to put that attachment at the end of our PDF for this PowerPoint. So whatever PowerPoint you download in PDF form, if you look to the end, I think we're going to have this kind of supplemental material where we provide the explanation on some of these lengths. And that's just if you're curious. What's nice about these is that these are standardized values. They shouldn't be changing unless the standard changes, and if the standard does change, we'll update our notes. So essentially you can take our word for it that this parallel length right here would be 27.5 feet prior to that taper. So that's what that is. It's a distance from the edge of that barrier to the taper beginning. Okay, and similarly to LP1, LP2 is also a parallel length, and that's also defined in the design standard. That comes from what we call our predefined length of what an approach terminal length would be. So for this case, looking into the design standard, the value is 56.3 feet. And again, we have some supplemental material to show you how we define that, but that's also standardized. But it's essentially taking you to the length from post 1 to the post just outside of what's considered that terminal length, because the post just outside of that length, the guardrail can then essentially bend a little bit and then start tapering as it's shown. And so that's another variable where it's standardized, it's defined for you right here. The default value actually would show 56.3 feet. And the same thing with LP1, by the way. The default value would give you your TL3 of 27.5. So most of the time you wouldn't even have to touch these, and that's what's nice. So the length of gating, LG, that's similar to the single-faced. That's basically 12.5 feet between post 1 and post 3. That would also be a default as 12.5. If you did have a non-gating version of this, then you can make the length of gating 0, and you have redirective capability at post 1. But that's only for that case, and you'd have to specially define that in your plans. So for the most part, you'd use the default value of 12.5 feet. The taper rate of crossover, so you see it's 1 and then TR. So what you're going to write in is that TR. So our taper rates are typically 1 to 10 or 1 to 15. We've given those values to you right here depending on your design speed. For greater than 45 miles per hour, you're at 1 to 15. For less than or equal to 45, you can use 1 to 10. And so you fill in one of those values. It's either going to be 10 or 15. You can look into the AASHTO Roadside Design Guide for more specific speeds if you prefer. And the rigid barrier skew is right here. This is something in the previous design tables. The skew of these rigid barriers was never really handled in all those pre-designed sets of guardrail. So now we're actually going to account for that. And so the idea here is that's just the distance longitudinally between the ends of these barriers. And if it's a positive value, if your input down here is positive, then it matches the drawing. So if your configuration looks like this, your value would be positive. If your rigid barrier underneath here on the bottom would actually be behind this rigid barrier up here, that S value would be negative. So that's how it works. So we've tried to explain that in the notes as well. And with that, we can move on to our Part D example. And the goal here ultimately is to have the information needed to fill in these callouts. We've given a callout to get started. It does make you think a little bit because in reality, you wouldn't start with one of the callouts already given to you. Because it's that way, we might actually work backwards on a few of these, but I'll provide the explanation for you. And also, at this point, I recommend, if you can, have this drawing in front of you and these explanations of the variables in front of you as well. So either you can print out your own version of the program, or you could look to our supplemental material we're going to provide at the end of the PDF of this training. There's a couple of different ways to do it, but yeah, it is nice to have that in front of you just to try to follow along. But I will explain the variables again as I step through them one by one. Okay, so for this example, we can see we have some givens. We have our design speed of 65 miles per hour. Our average annual daily traffic is 10,000 vehicles per day. Clear zone is 36 feet. We got that out of the PPM table 4.2.1, given these criteria above. And the terminal type equals gating. And so whenever we see a terminal type of gating, we start thinking about that 12.5 feet. All right, let's take a stab at some of these program inputs. So the first one would be direction of traffic. We're designing for this as a hazard. You can see where the departure line is, and so the vehicles are coming from right to left. North arrow is here, so we got westbound traffic. The ADT, that's given up here. We just go ahead and fill that in as an input. We'd also put the design speed into the program as well. Those are just given. All right, so our next input is the face of the rigid barrier. What is the station for the face of the rigid barrier where the guardrail is connecting? And so automatically we start looking up here. We see that we've been given some information. The begin guardrails at station 100. So is that the answer, station 100? The answer is no, it's not, because we remember we have this little bit of a difference between the edge of the rigid barrier and where the guardrail is considered to begin. So typically, the first thing that you start with is that edge of the rigid barrier. And you wouldn't be worried about having a nice even round number as a station. We just happen to give that to you. And so this does seem a little strange because we're kind of working backwards. We gave you this nice even round number for a guardrail station. And so now we're going to have to spoil that nice even round number a little bit and work backwards to give you the face or the edge of the rigid barrier. And so if you remember, the difference between the two is 7¼ inches. That works out to be this little decimal here. And so we gave that to our classes going around and training in all the districts, just to make people think a little bit and think backwards about how the stationing works. But for the most part, it's more simple than that, because the first thing you're going to have to work with is the edge of that rigid barrier, and you just go ahead and fill that right in. And then the beauty of it is that it will back calculate where the start of the guardrail is for you. The original offset, LO in this case, well, we show 10 feet. Looks like a 10-foot shoulder, so that just continues right along there into that face of guardrail, and that's what we're concerned with, and that's prior to any type of taper. Okay, so some more inputs. Our lateral area of concern, that equals 32. And so, okay, how did we get that? Okay, again, we're talking about this lane right here, the traffic going right to left, and the clear zone is 36 feet. So this rigid barrier across the median is well within that. How do we know that? Okay, the back of it is 10 feet plus 22 feet. It's 32 feet away. And that just also happens to be our lateral area of concern because it's well within the clear zone. Remember, LA, you have to design for the lesser of the two, the extent of the clear zone or the back of the hazard for the most efficient guardrail design. And so you can go ahead and use the value of 32. Parallel length 1, or LP1, it's 27.5. And the quickest way to get that is we'll just go back and look right here. So LP1 for TL3 is 27.5. We know our design speed is 65 miles per hour, and so we're just going to go ahead and assume the TL3 is going to be needed, and that will be the default value anyway. So 27.5. And just as a reminder, that's the length from the edge of the rigid barrier here to the point where that starts tapering. It's a parallel length. LP2, 56.3. I'm not going to click back to the previous slide to show you that again, but you know that this is given to you in the notes, and that's the length where this guardrail taper begins right here, and then all the way to post 1 is 56.3 feet. That's per the standard, and we've defined that for you. The length of gating, as I said at the very beginning, when you start talking gating terminals, pretty much across the board, all the APL drawings have essentially 2 post spacings, 6 foot 3 inches. That gives you 12 foot 6 inches, 12.5. The taper rate is 15, and you can get that out of the notes next to the input that lets you know that if your design speed is greater than 45 miles per hour, which it is, your taper rate needs to be 1 to 15. And then the bridge skew, it's drawn in the direction of the diagram on the previous sheet, and so you know that's a positive value, and so the difference between these two is 8 feet. And that wraps up the input variables. And what's nice, it's a one-step process. Put those in, and then you're going to get some outputs. So moving along to our final output sheet now. And you see we've been able to fill in some of our call-outs based on the outputs of the program. And so you remember we had put in the face of the rigid barrier at 100 plus 0.6. It then back calculated the actual start of the guardrail, which is a little bit prior to that because the stationing is increasing going left to right. So that rigid barrier station was slightly higher. And so you can see your begin guardrail, nice even round number, station 100, just as it's shown up here. And then what happens is, just as with parts A and B, all of our offsets are again measured from the edge of that travel lane that we're concerned with. And so it's giving you offsets of 10 feet and 10 feet for these two guys, and 16.7 feet and 16.7 feet for these two guys. So that's what's kind of nice too, is these two offsets will always match and these two offsets will always match. These are measured from the edge of travel lane. If you did the math and you assume the center line is directly between these two barriers, that'd basically be an 11-foot difference. You can quickly figure out what that offset would be. So here it's actually showing you 11 feet and 11 feet measured from the center line. And then here the difference between those two is 6.7. Difference between those two is 6.7. And so that's how you get that. But in reality, when you're drawing your plans, you could just measure from the edge of the travel lane, and then your plan view labeler will give you the actual offset from the center line. So your plan view labeler does just take care of that for you. So now something we've done to make this a little more simple than the part A and B in terms of laying this out. These calculations are far more complex because we're automatically taking a lot of things into consideration to design this crossover. The taper rate has a direct effect on the length. It's a fairly complex process. The other thing we do, as I'd mentioned in the IDS training, is that these panel lengths of the diagonal portion between the two parallel lengths are adjusted to the nearest panel length. And so that way we consider this, buildable in the field, very closely to how it's shown in your plans. Or at least if this was all parallel, it would actually be very close to being exact if it was all parallel. And so the idea was to get as close as possible to reality. And now I just mentioned curvature. So the way we handle it here is if there is curvature on the roadway, the idea is that it would likely have a lot less effect on the conflicting difference between the distance from station to station versus the actual guardrail length. The reason for that is because we're dealing with medians. Most of the time a center line would be on the median, and we would hope that's the case. It's a lot closer. The time you have a real discrepancy is if you're on the outside or the inside of a curve, divided highways, and there's a big lateral offset difference. In this case, we would be expecting the lateral offset difference would be pretty minimal. But even so, we can handle some extra curvature and still be okay. We know that we've designed this to be conservative. And so the idea is that if all of these stations and where these actual posts would end up are within 3 feet of what it's going to be for the contractor in reality, then that will be acceptable. And that's per the new specification tolerance in 536 that we spoke about. So we were really trying to make this simple for designers and say, hey, here are your outputs. Go ahead and use them in the plans, and that's fine. If you anticipate a very strange situation where your center line is just way, way off center, very far away from this, and you have a very, very tight curve, then you may want to reconsider looking into some of the math behind this and extending it out to make sure that your length of need is covered. But really, it's nice because at the very least, we gave you some guidance that would be the minimum, and then you can decide if your curve would extend it or not, and you can just extend it, the length here and there, and that's the beauty of you have the control over it. You can extend this out if you'd like to. If you just went out another 20 feet just to be on the safe side, you're in the ballpark. And that's really all we're talking here with guardrails, to be in the ballpark, err on the side of being conservative. And that's really all there is to it. So we're trying to put some power back to the designers with allowing you to actually use the calculations and work with it, as opposed to just trying to figure out which scenario in the table applies to you. And then there was a lot of concern and people wondering over if the contractor is supposed to just use the table or if the designer is supposed to tell the contractor how to use the table. And now we're putting the design back squarely in the court of the designer, and that's the idea. Contractor should just have to follow station and offsets. Okay, and that concludes our guardrail length of knee training. We're just essentially trying to give you a feel for it. And really the way to get to know any program is just to go in there and play around, mess around with the variables yourself and see what you get. Hopefully you can't break it. We tried to test it in every possible way. But if you do see any issues, please send us an email. I'll give you our contact information in a minute. Okay, so just wrapping up the training, we wanted to let you know this could be in your printout. This is in the PDF, so you have this link. You can also just Google search FDOT contact mailer. The idea is if you want to be notified about trainings like this in the future, please feel free to sign up in the contact mailer for the design standards having to do with roadway or any other interest you may have. So that's just an advertisement for that FDOT contact mailer. It's pretty useful for hearing about trainings like this one. So with that, we want to say thank you for your interest in Guardrail. We can't really field any questions right now really quickly, so you can't try to stump us. But we do have our contact information here right at the bottom, and so we're hoping if you think of any ideas, if you thought of any ideas along the way in the course of our training and you had some questions, please go ahead and send me an email. Alternatively, Durwood Shepard is pretty knowledgeable about these things, and so his email address is down here as well. And thank you for watching our training.